Last night I posted some additional materials. So let me just, I didn't have time to send out an email. So if you get a Stat 512 to the class schedule, I did post the lecture, and I've updated the syllabus for this class schedule a little bit. I didn't have time to finish the .or markdown. Sometimes it's pretty easy to go from a .ornw file, which is R embedded within LaTeX, to a .ornd file, which is R embedded in Markdown. For various reasons, it's not quite so simple on this particular assignment, and so I will do that. Part of the problem is that this course was kind of an add-on for me, and the other course takes a lot of time. And I also gave an assignment there, and that was pretty easy to convert to our Markdown, whereas here it's not. But I will do it. But again, work on what I gave you, and I'm going to want it electronically submitted to me. So what that means is that on the ones where you have to compute things more like a calculator, probably the best way to do is to use R as a calculator, and therefore it's reproducible. And there are other ways you could do it. I mean, you can cut and paste, but it's not reproducible. So I would prefer you to use R Markdown, but I will give you the template either tonight or tomorrow night, hopefully tonight. I've had a lot of things due the last few weeks, and so I'll try to get it out tonight so that you can use that as a template. In the meantime, you can kind of use some of the Markdown documents that I've given as kind of a template. The main thing to remember, and really the only thing you have to do, is put the 3 tick marks and then brackets with R in it. You don't really have to name the chunks unless you're referencing the chunks from another chunk. The reason you label a chunk, there are 2 reasons why you have additional arguments within the curly braces. And one is if you put a label, then you can reference that chunk from another chunk. And the other reason is if you have options, like if you have figures, you can talk about the width and the height of the figure, and you put that, as arguments within those curly braces. And then you end the chunk by 3 ticks. So really, to just do the code, you don't really have to, the textual part, if you have to explain something, then you just do plain text, much like I'm doing, with the assignment. So at any rate, I will post that assignment soon with the R Markdown version of it. So I want to go into our studio. And a few things I want to do. I'm going to blow this up to full screen. And I'm going to clear the console. So let me go into 512. We're going to look at chapter 9. We started this last time, so we're going to continue that. So chapter 9.ormd. Now, another thing that you should always get accustomed to is set the working directory to where you are located so that your global space where you save things are in this case, in Chapter 9. If you want to see if there's stuff left over from a previous session, you can clear it, so you start out fresh if you want to clear that space. So that is the environment that if I create variables, it's where they will appear. Now you may want to note that if I just knit this, so if I just knit this, so that hopefully, yeah. So this actually creates the whole file, but you'll notice that even though I created variables, they didn't get put into space. And when you knit something, they don't. But if I execute them one by one, they do. So the workspace, so when I create an object, an R object, if I do it one by one, they get saved. Or if I create it in the console on the right, then you will have the objects you create saved in the workspace, and you can see what they are. So I often tend to leave the workspace open. Once I have opened the file, then I often click over to the workspace. It depends on how much space you want to see, because sometimes if you're programming, you want to sort of maximize the amount of code that you can see. Okay. And again, we can kind of switch back and forth and look at the different views of it. So just to go back to this view for a moment to see where we were from last time. We're talking about simple linear regression, and basically it's when we have measure pairs of variables, so we're measuring an x and a y on the same experimental unit. And in this chapter we're going to assume that they're both numeric, that is, sometimes we call those continuous random variables, although in some cases they may be numeric but discrete, that is, like a count. But we're going to assume that that we have both an x and a y. Now, in a design regression experiment, you would fix the x and measure the y. But in most cases, both x and y are random. Now, technically, the regression model is built under the assumption that you have a model right here above the arrow. Y is alpha plus beta x plus epsilon. So that's a very simple model. And you're assuming actually that x is fixed there. It's not random. But in reality, x is often random. And so what we do is a conditional model. And we look at the conditional expectation of y given x, which is alpha plus beta x. And it turns out that in terms of the null hypothesis we test or the inferences we make, they're essentially the same. Where they differ is when you actually compute things like power. In other words, if they're both random, then when we get into type 2 errors, which is the probability accept when you should reject, when you compute power, the power is, if you call that beta, beta is the probability that you accept when you should reject. That's type probability type 2 error. 1 minus beta is the power. It's the probability to reject when you should reject. When you compute things like power, that does depend upon the assumption of fixed x. But under the null hypothesis, it doesn't matter. So we had a least squares principle. In other words, we don't know alpha and beta. Those are parameters, and we don't know them, so we want to estimate them from the data. And so if you think of a scatter plot, you're going to draw a straight line in it. Then alpha A will be the estimate of alpha, which is the intercept, and B will be the estimate of beta, which is the slope. So that's pretty simple, but how do we determine it? Well, we're going to use the least squares principle, which says that the sum of the y sub I minus y hat sub I, or y hat sub I, is the predicted value on the regression line for a given xi. You're going to assume that that difference, if I square it and sum it over all the values for I, I equals 1 to n, then you assume that you want to minimize those vertical lines, which are the deviations of each point from the regression line. You want those vertical lines, that is the absolute values of those, squared to be minimized. Now, that's called L2 regression, by the way. If you minimize the sum of squares of the y minus y hat sub i's, that's called L2 regression, or least squares regression. L1 regression is when you minimize the sum of the absolute values of the y sub I minus y hat sub I. Turns out that that's actually a harder problem to solve. And the reason is because for those of you who know calculus, if you have some x squared and take the derivative, it's 2x, so it makes it linear. So it actually turns out that because we're differentiating, to find the minimums, we're differentiating these with respect to a and b and setting the result to 0. Turns out you end up with a linear system of equations in the number of however many parameters you're going to estimate between the cases 2, alpha and beta. So we would get 2 equations and 2 unknowns if we actually use calculus and differentiate it. The resulting linear sets of equations are called the normal equations. Now, I'm not spending class in this time to go through that. In a more theoretical class, you would do that. So if you do solve for beta, for the case where you have only 2 equations and 2 unknowns, we can solve this directly. And we get that beta is the sum of cross product deviations over the sum of squares of the x's from the mean. And so we call that the numerator, which is the sum of the cross products of the x's and y's adjusted for the mean. We call that s sub xy, and then the sum of the x minus x bar squared, which is sort of like, if I divide that by n minus 1, that would be like a variance of x. We call that s sub xx. So that's the sum of squares of x, of x with itself, where s sub xy is the sum of squares, so the sum of products of x with y. But again, they're adjusted by subtracting out the mean, or we could say they're centered about x bar and y bar in each case. So that turns out to be, I give 2 expressions to that. One expresses it in terms of deviations, and one expresses it in algebraically equivalent form. The second expression, the sum of the xy's minus the sum of x times the sum of y's over n, those expressions are much easier to do on a calculator. So if you actually did it by hand, then that would actually be much easier to do. Now, there's not a lot of reason to do this by hand, other than the fact that you might want to do it once to say you've done it. But we used to have to do this by hand back in ancient history. So there are all sorts of clever ways. See, the normal equations, this is 2 by 2, that is, there are 2 equations, 2 unknowns, but in multiple regression, you may get k plus 1 equations and k plus 1 unknowns, where k might be 10. And so if you have, that would be the case, where you have, k predictors trying to predict y. And for that case, if k is very large, that can become burdensome, but there are actually some pretty clever numerical techniques that were worked out that allowed you to do it by hand. Back in the days, it went through this evolution, from a slide rule to mechanical calculators, and you used to have rooms full of people calculating things. And you had to have multiple people do it because they had to check each other because the opportunities for error were great. But there were some pretty ingenious algorithms that were developed. One is called the abbreviated Doolittle method, for example, that actually, back in sort of the 7th or 8th grade, where you had, when you first took algebra, when you had substitutions or when you had a simple set of linear equations, there were very simple ways to solve for it. And as I said, that's fine as long as you have 2 or 3 equations and 2 or 3 unknowns, but not so good when you get more than that. At any rate, it turns out that allows us to solve for A and B. We do actually have to estimate, there's another parameter that's not known. Can anyone tell me what the other parameter is that's not known?
Is epsilon.
What now?
Epsilon.
Well, epsilon's a random variable, so what's the parameter that I'm worried about? I don't actually specify it there, which I probably should add that. Epsilon is a random variable, and we typically assume that it's normal. Although you don't have to assume it's normal. There are other assumptions we can make about epsilon, but typically the standard regression, we assume it's normal with a mean of 0, and that would be true if the model alpha plus beta x, which is the mean of y, if that's really the mean, which does depend linearly on x, then we can say, well, epsilon has mean 0, but it has variance sigma squared. So sigma squared is the other parameter you have to estimate. Now, so far, you don't have to estimate it to get the fit. You can estimate the slope, just A and B, and you plot it. So you don't need it. But as soon as I test a hypothesis now about B, for example, so beta. If I want to test that beta equals 0, the slope is 0, then I need the estimate of sigma squared. So, and you're assuming, this is a key assumption, I should add that. You're assuming that sigma squared does not depend on x. So there are two things here. We have the mean of y, which is alpha plus beta x, which says we're assuming that mean linearly depends on x. So as x gets bigger, assuming that beta is not 0, either the line goes up or it goes down, and beta is negative. And so we're assuming that the mean linearly depends on x, but the variance, sigma squared, does not depend on x. Now that assumption may be violated, and that's something we can check. So, so at any rate, so the first thing we may want to do is sort of estimate this. So if we go back here to, I'm sort of going to kind of continuously being updating these .OND files. And when I do, I'll let you know that there's a new version up there that has some additional information in it. This is kind of a work in progress. By the way, have any of you heard of the Kahn Institute? Kahn Institute. Kahn, I believe. Have you heard of it? You know what it is? What?
Teaching videos on YouTube.
Yeah, it's teaching videos on almost every topic, and there are really tens of millions of people around the world taking Kahn courses or supplementing in-class courses. And the idea that he initially had a relative that he was in, I don't know if it was New York or where he lived, but he had a niece or something who lived in Louisiana or someplace, and she was having trouble with math, so he was trying to figure out a way how to help her tutor her. And so what he did was he would by hand sort of work out problems and talk, and it was recorded. And much like me here, you didn't see him. What you saw was what he did, and you heard what he said, which is the same philosophy I'm using. Well, it kind of caught on, and now there are courses on almost everything. So if you want to review calculus or algebra or matrix algebra, it's not just math though. It's on economics, you name it. And so there are all these there are all these videos that you can work through with him. And they have actually substantial backing now, and they're doing what they're calling flipping the classroom. And what flipping the classroom means is, and it's ultimately sort of the model I want to move towards, is that you actually give the lecture and post it, and then use the classroom, if you're in class, to sort of work out problems and things like that. So you don't really lecture in class, you may work problems, and it's sort of like a lecture, but it's... and so actually some school districts are adopting this approach. So now if you look at Coursera, and this again is the model I want to move towards, is if I took this course and did it the way that Kahn does it or Coursera does it, I would have little 10-minute bursts of video. Like each section would be a separate video, so it would be 10 minutes plus or minus 2 minutes or something like that. With the idea that no one really wants to listen to a 75-minute video, not in one sitting. And if you want to find something, and if you say, okay, this is section such and such, and here's a 10-minute video on it, you know that's the section and that's the video, and you don't have to hunt. Well, at the 45th minute of this 75-minute video, you can find this topic. But you don't know where that is, so you kind of have to search. And so that's the problem with what we're doing, but again, it's going to take maybe one more iteration to get to this point. So what you have is many 10-minute videos. And that, I think, is actually a good idea. And so basically, within this context, essentially every section would become a separate video as opposed to a chapter. But at any rate, I think that, I've thought about the fact that essentially every course I teach now, I'm going to teach online simultaneously. And again, that's what I want to move towards, that type of model. And I've thought about the fact, can you teach a theoretical course online? Because here we can, because we can use R. And so people can work along with you, and you actually could use other environments in the same way, like SAS or SQL type programming, or even programming like JavaScript or whatever. Yes, you could do it. And so I thought about, how would you teach a theory course using this method? Because I sort of had the opinion previously that the only way you would teach a theory course is in class, not online. I've kind of changed my mind about that. And the reason I have is because of software like Mathematica. Because Mathematica, you can do in theory what we're doing with applications. So at any rate, I think that it would be possible to teach theory. But let me get back to this. So what we're doing here now is I'm going to execute, and so I created a data frame called BP. And I'm going to sort of bring this up right. So there's BP now. And I'm going to attach BP. Now, by attaching BP, what did it do? Well, if I go over here and say search, then BP is actually in the search path. So if I have a symbol in R, then the question is, how do I determine the value of that symbol? So for example, I have a variable age, and if I would not have attached it, and I tried to use the symbol age, what would R have done? Prior to attaching BP, what would R have done if I used age in an expression? It would have looked for it. How does it look for it? It looks down this. It would look in the global environment and says, there's no age. So now, forget about this. It would then go here. It would keep looking down, and ultimately it would say, I can't find age. Symbol undefined. By attaching it, when I say ls, what ls is going to do by default is return the global environment, what's in it, which at this point is just BP. But if I say ls of 2, it will return, each of these is an environment, and it will return these symbols in the second search, in the second position in the search path, which is BP. So if I say ls of 2, now if I use age in an expression, although it doesn't find it here, it finds it here. So it does find it. So that's a key thing to remember. It can get you in trouble if you don't realize it. Okay, now I'm going to, you see I'm actually creating n, which is the sample size, so n is the dimension of P, and I'm selecting, the dimension is two-dimensional, it has rows and columns, because BP is a data frame. It's sort of like a matrix, except the different columns can be of different types. They can be numeric or character. And so I create another symbol n, which is now in my workspace. It's my global workspace. I use a function dimension, which is two-dimensional, and then the square brackets say I want the first element. I have a vector. Dimension of VP is a vector of length 2, and the square brackets with 1 says I want the first one, and it says the first one is the number of rows, and that's the number n of observations, which in this case is 10. And so the next thing I do is now this is a little more complicated. I call a function called LM. LM stands for linear model. And so I have a linear model and I say systolic BP tilde age. So what's happening here? The Y variable is the systolic blood pressure, and I'm trying to predict it by age. Does that make sense? And what I'm saying, think about the tilde as being is modeled as. So we're saying systolic blood pressure is modeled as a function of age. In this case, it's a linear function because LM fits linear functions. That's what we mean by linear model. Now, linear model can actually fit very complex linear functions, but they're still linear in the parameters. When I say linear, I mean linear in the parameters. So it's linear in alpha and beta. So I'm going to now create an object called fit BP. So that object doesn't automatically print out, but notice that I could print it out, and now notice that fit BP is now an object that I've created. So let's just print it out and see what it is. So if I print this object, it will have a default. If I put a object on the line that I've created and I just type it, it will have a default print function applied to it. And the print function is often pretty simple. And in fact, it's simpler than what we probably need. But what this gives us at this point is when I just say that, it says, okay, here's how it was called, LM formula equal the formula. That first argument is actually a named argument called formula. So formula equals systolic BP tilde age, and the coefficients. So there's the intercept. That is A is 53.69, and B is 0.618. So we're saying it has a positive slope. And so you might ask the question next, if you're sort of interactively doing this, and I could interactively do this over here, but I didn't. I embedded it over here so that I have explanatory text around it, which is sort of the way I want you to do your homework. So if your homework says explain something, then you've got a chunk of R code that you did the analysis, and then you have some explanatory paragraph. Just type. You probably won't need equations for the most part.
Do you want us to typeset things into the formulas for like solving?
You don't have to. You mean like the normal equations? Or?
Yeah.
No, you don't have to give that. Now, if I see the R code, how you did it, as I said, you might get some enumerated steps, but you don't need to go back and sort of, I'm sort of assuming, well, I mean, I didn't go into the details of the normal equations, but at any rate, you don't need to get that level of detail, because I'll usually explain why something, or maybe interpret the results. So you don't really have to explain, again, that you might, I don't want to see just the answer. So if you're doing a two-sample t-test, I don't want you to just give me the t and p value.
Right.
You should give a little bit of R code to confuse them. Okay. Of course, in some cases, I'm not saying you can't use t-dot test, but t-dot test only works when you have data. If I give you the mean and standard deviation, you're going to actually have to use R-Pound's calculator. Right? Is that sort of the question you were asking?
Yeah.
Yeah, like if you only have Y bar and S, you're going to have to use R as a calculator. But if you've got the raw data, you could use t-dot test. Okay. So it's always a good idea to plot. So the first thing you might want to do is just plot. And if we do this, let's kind of expand this up. And then AB line, when I put the model object, which is fit BP, when I put that as an argument to AB line, for certain model objects, it extracts, in this case, it's a linear equation, so it actually knows how to extract the slope and intercept to draw the line. So if I do that, okay. I did the, so fit BP is an object, it's a model object. So what are the attributes of those objects? Well, coefficients, fitted values, residuals, and so forth. Those are, and it's the class of this object is LM. Now, some objects will actually inherit from a class, which in turn inherits from another class. This is called multiple inheritance. But LM, linear models, is any object that's created with the function LM will be of class LM. And how else could I extract the coefficients? Suppose I just wanted the coefficients and I wanted to use them directly. So I could do fit BP $COEF. And if I do that, it actually just extracts the coefficients. So that's another way I could have extracted the coefficients, and I could have passed it to the AB line that way. That's just a vector of length 2. And notice that the vector has names, intercept and age. So it's a vector, but the elements of the vector are named. So I could extract anything I want. So I could take fit BP and I could extract the residuals, and those are the residuals. Later on, we're going to plot the residuals. So these are the $sign as an extraction operator, and notice that I don't need to write coefficients out as long as it uniquely matches. So I can have partial matching. So when I did fit BP $COEF, I didn't really need to write coefficients out completely. I could use partial. As long as I go far enough that it's unique, I can use partial matching. So I could get the fitted values, and the QR, that means QR decomposition in matrix lingo. And the QR decomposition is actually an algorithm that is used by linear models to actually compute the coefficients. So some of those are a little more technical. So going back, suppose I wanted to estimate these things by hand, then I've actually done it two ways. Sum of S sub xx, this is the computing formula. If you would do it on a hand calculator, if you were doing it on a hand calculator, you could do the sum of h squared. So the caret represents squaring. And what happens is that, just to show you a little bit more of R, that if I take age and I square it, there are 10 of these, and it's vectorized. So when I square age, it squares each element in age. And then when I do the sum of age squared, it reduces it to a single number. So the sum is a function that reduces a vector to a single number, which is the sum of the elements in that vector. So that's the sum of squares of, that's like the sum of x squares. So I actually sort of put those all in one step. The sum of x squared, it's almost like reading the algebra, right? The sum of x squared minus the sum of x, the quantity squared. Notice the caret is outside the sum of age, divided by n. If you're not sure, there are precedence rules for all these operators. If you're not sure of the precedence, then you should enclose in parentheses to make sure. But there is a precedence you probably should learn. So at this point, let me go ahead now and compute the sum across the corrected cross products. So at this point, I have S sub xx, which, what happened here? Why didn't it put it in? What now?
I think you just skipped that line.
Oh, I skipped that line. I did it. Oh, okay. So there it is. And I'll do that again. And now if I type out S sub xx and then S sub xy, then those are what are computed, right? Now, I do it again, and this time I'm giving the other formula where I take age minus the mean for each element. Again, age is a vector, and the mean. So this, you may think this is funny. So you have age, which is a vector of length 10, and I subtract off the mean of age, which is of length 1, right? But R also has, besides vectorized arithmetic, it has a recycling rule. So if I'm subtracting something of length 1 from some vector of length 10, it recycles that mean for every element in that vector. So the mean actually gets subtracted from each value. So if I subtract the mean from each value and then I square it and add it up, that's algebraically equivalent. So I could do that right here. And then if I look at the values, so I did it differently. So there's S sub xx and S sub xy. And of course, those are exactly the same answers. So in other words, we kind of verified the fact. That the second, when I say b equals, that the first expression on the right is the same as the next one, algebraically. So I did it both ways. So again, if you use R as a calculator. Now, of course, we don't really need to do that because we're going to just fit LM. We don't need to compute these. But it does show you that R can be used as a very powerful calculator. So again, continuing to use R as a calculator, I now compute, I say B is S sub xy over S sub xx, but I'm also going to round it off to 4 digits. Some cases it prints out too many digits and you want to round it off. And then, so if I now print out B, you can see that that's, why did it not round it off? Oh, it didn't round it off. I'm sorry, okay, this is a good illustration. When I executed round B, and I have parentheses on the outside which prints it out with 4 digits, right? But if I just put B, it prints it out with more digits. So a lot of times, if you want this to appear in a report, you'll surround it by a round function with the number of digits as a second argument. So now A, of course, is the mean of y minus b times the mean of x. And again, I'm going to round it off. So there is, there's the intercept. Did I say B? Well, no, I said A. Yeah, A is the intercept, and we just computed it. So we computed this all by hand, but as I said, obviously this is typically not what we're going to do. Now, the actual model where is it? The actual model is right above my arrow there. That's my prediction model, and I have y hat to indicate that if I put an x value in, I'm going to get a predicted y value out. So if I put in an age of 10, I would get out a y hat for that value of 10, x equals 10. So any questions on that? So the next thing you typically do is we're going to assume that x is fixed. Well, in reality, it's often not, so we consider the model conditionally. Yeah.
Yeah, actually, I'm asking if you want to calculate the regression coefficient R.
Compute what now?
Regression coefficient R.
You mean like the correlation coefficient?
Yeah.
Yeah. Right.
We do the same thing.
It would be very simple. You would need one more thing. You would need S sub y. In other words, you would need the sum of the y minus y bar squared, and then you can compute the correlation. We're going to do that later in the chapter. Okay. So the question was, what happened? Can we compute the correlation coefficient? The answer is yes. You can also compute a measure of fit called R squared. And again, later in the chapter, we'll look at this. Here, actually, I do define the distribution of epsilon. So basically, if you're going to predict, you want the slope to not be 0. If the slope is 0, then the prediction is always what? If beta is 0, And if the corresponding, even if beta is 0, the b wouldn't quite be 0 because of random variation. But if beta is 0, then you really have no predictive power because when you fit it, if in fact b, if b would be 0 or close to 0, then your estimated y is always about y bar. So you would estimate the mean. So you wouldn't have any predictability because, in other words, by knowing the age, it wouldn't tell you anything about systolic blood pressure if there was no relationship between age and systolic blood pressure. So we're assuming that beta is not equal to 0, which gives us predictive power. Now we actually can test that hypothesis. That's what we're going to do in a few minutes. So we actually want to test the hypothesis that beta equals 0 versus, well, I say versus not equal to 0, but it could be one-sided. You could test it's negative or positive. So, but you could also test that beta, you could test something other than 0. Suppose you wanted to test that the slope is 1. So you could test that beta equals 1. So I say you could test beta equals beta naught, where beta naught is specified by u. You don't have to test that it's 0, but that's usually what we do test. But we can do it more generally. So we're assuming x is fixed, and technically we can kind of get around that assumption in terms of the null hypothesis we're testing. And we're assuming that epsilon is independent and identically normal with mean of 0 and a variance of sigma squared. So I do have it down here. Now, you notice my notation over on the right. I say epsilon is distributed as, the tilde here means is distributed as, IIN. So what does IIN mean? Independent and identically distributed as a normal, with a mean of 0 and a variance of sigma squared. So the variance does not depend on x, unlike the mean, because the mean does depend on x. The expected value of y, which is the mean, is equal to alpha plus beta x. Now, if I don't assume that epsilon has 0, then the mean of y given x will not be alpha plus beta x. It'll be alpha plus beta x, whatever the mean of epsilon is, which will shift it. But again, we incorporate that mean back into the model. And if the model is not correct, in other words, if the alpha plus beta x is not correct, and we can look at that assumption, then in fact, we maybe need a more complex model. Maybe we need a curved model or something like that. So we need to check all these assumptions. So how can we can test this with a t-test. So in chapter 8, we talked about t-test. And basically, if you were testing mu equals 0, what was a t-test? Well, in its simple form, the t-test was y bar over the standard error of y bar. So you can think of it as y bar over standard error of y bar, which is s over the square root of n. And that would be testing the hypothesis that mu equals 0. If you were testing at mu equals 10, then it would be y bar minus 10 over the standard error of y bar. So this is basically the same thing. I'm testing that beta equals beta naught, and so I test it by, well, if beta naught is 0, I'd simply test it by b over the standard error of b. It's actually the estimated standard error of b. And that's why we need the estimate of sigma, the Greek letter sigma. Because the standard error of b is the standard error is sigma over the square root of s sub xx. By the way, if the data is too concentrated about x bar, then s sub xx becomes very small, and therefore sigma hat, which is my estimate of sigma, over s square root of s sub x becomes, if s sub xx approaches 0, okay, then that standard error gets very big. Okay. And that's because the regression coefficient has to have support. In other words, there's a range of x values, and if that range of x values is too small, the regression line just kind of flops around on top of it. There's not enough support. So when you're designing an experiment, if we design it and choose x, we want to make sure that there's an optimal way to choose x if you're actually designing it and can fix x. Then there's an optimal way to design it such that you have enough support. Because if you don't have enough support, then you get into trouble. The standard error gets too big, the t-test gets big, you're never going to reject. So now again, I have sigma hat, the standard error, or the estimated standard error. The difference between the standard error and the estimated standard error. You notice I have written the estimated standard error b. The standard error b is sigma over the square root of s sub xx. The estimated standard error replaces sigma by its estimate, sigma hat. So then you ask, well, what is the estimate? Well, intuitively, it's the amount that the y's vary vertically from the y hats. How much, if I go back, the estimate of the standard error is related to the vertical differences between the points in the line if I project straight down so that the vertical differences are parallel to the y-axis. So if I take the sum of squares of those, that's the measure of the variation about the line, which is a measure of sigma squared. If I take the vertical differences and square them, add them up, it's a measure sort of sigma squared, except that I have to divide by some function of n. Now, if you were estimating a single thing, like when you estimated mu and you asked the variation, how do points vary about mu? Well, there was only one parameter. Because of that one parameter, you actually divided the sum of squares of y minus y bars squared over n minus 1. That minus 1 said we were estimating one parameter. We lost 1 degree of freedom because of that. But here, we lose 2 degrees of freedom because we're estimating 2 parameters, alpha and beta. So we can think of the variation of these vertical differences. If I square them and add them up, I want the line that minimizes that, and the variation about that line is the estimate of sigma squared. Now, when I do the standard error, it's actually taking a square root, and that's why I'm interested in sigma. But again, I divide by n minus 2, so because I'm estimating 2 parameters. So if I look at this, and if you look right above, right there, intuitively you can think that I have s squared of y dot x. What does that mean? What does y dot x mean? S squared of y dot x. It means I want the variation, but it's from this linear model that depends on x. So I have y dot x means I'm fitting x. So I want the variation about that line. So I have the sum of the y minus the y hats squared over n minus 2. The minus 2 reflects the fact that I have to estimate 2 parameters, alpha and beta. Now, there are computing formulas for this. If you've already computed s sub yy, if you've already computed s sub yy, s sub xx, and s sub xy, you can actually get this in a couple of ways. You can get this as, and this is not so intuitive, the first way above the error intuitively makes sense. The other ways are if you were doing it by hand, and you've already computed the s sub xx and the s sub xy, s sub xy, and then you also, s sub yy, so all three of those quantities. Then I could take s sub yy minus b times s sub xy over n minus 2, or I could take s sub yy minus s sub xy squared over s sub xx divided by n minus 2. Either one of those will allow you, I'm simply, in the last expression, I'm simply putting in the value for b, which is s sub xy over s sub xx. So I'm just substituting for b to go to the last expression. Okay, so, and here I've defined the s sub yy. And so now, in order to get that denominator of my t-test, I put s sub yx in the numerator of the estimated standard error divided by the square root of the s sub xx, which is the s sub xx is the sum of the x minus x bar squared. So, well, fortunately, you don't really have to do that because there's another function called summary. And so if I go down now, if I go down and look at summary, So summary of the fit. If I just put fit BP on the line, it gave me the regression coefficients, but it doesn't give me any more. So if I say summary of the fit BP, that gives a lot of stuff. It gives the formula. It actually gives something about the residuals. It gives the min, the max, the quartiles, and the median. So the median residual should be about 0. You're going to have some plus residuals and some minus. By the way, the sum of the residuals equals 0. The sum of the y minus y hats equals 0. That doesn't mean the median or the mean. Well, actually the mean will be 0, but the median may not be 0. And so it gives the quartiles of the residuals and the min and the max. So the maximum residual is 8.34, and the minimum is minus 4.7. You can kind of see, you can kind of see where that might be if you look up here. The max is probably this one, and the minimum might be this one right here, which is negative. So if I look at the output, now I have the coefficients given, the 53.69 and the 0.618. I have those two coefficients given, but I have a little bit more. I've got the standard errors. Now, I haven't talked about the standard error for A. In other words, the standard error of A, which estimates alpha. I haven't talked about its standard error because we usually don't test a hypothesis about the intercept. Sometimes we do, but it's rare. Well, here they actually give the test that alpha equals 0. But a lot of times, that's highly significant because it's rarely the case that alpha equals 0. There's theoretically some models that you expect the line to go through 0. Theoretically, you expect it to go through 0, and therefore you may want to experimentally test, and in fact, alpha equals 0, but it's not common. So what we're usually interested in testing that beta equals 0, and so now we have the estimate, which is 0.6187, and the standard error of that estimate, which is 0.1545, right? And so what is a t-test? It says take the estimate divided by the standard error, and that's a t. And that's a t with n minus 2 degrees of freedom. So the t-value is 4.004. That's the t-value. And then the p-value corresponding to this two-sided test, is 0.0039. So the p-value is less than 1%. So it's highly significant. So what we're saying is that beta is almost assuredly not 0. So in other words, notice the two asterisks after the 0.00393, and that says that it's significant at the 0.01 or 1% level. And again, we're assuming a one-sided test. The residual standard error. Well, let me compute a few more things here. So I'm going to compute. I can compute. Well, you tell me, what did that compute? Systolic BP underscore hat. I just named it that. And I said it's A plus BX, B time age in this case. So we now know over here, we now know A and B, and we have a vector age someplace. Well, it's actually evaluated in the next in the next environment. And so we get the y hats that way. I could equally have so I can get it this way: SYS TOLIC BP underscore hat. What did I do? Did I misspell it? Oh, SYS. Or I could have said fit BP Oops. I think it's predicted way up here. Where did I do the attributes? I think it's predicted. Thought I did that. Oh, fitted, yeah. So if I simply get the fitted values, okay. Now the fitted values, I don't know if you can see them both, but the fitted values here, extracted this way, are the same as what I computed up here. Now the residuals, which I also compute over here, so let me compute the residuals. The residuals will be what? That will take, the residuals will take the y minus the y hat. So I have systolic BP minus systolic underscore hat. And so that will be the residuals. So let's compute the residuals. And then I can print those out. Try not to misspell it. So those are the residuals, and if you look at those residuals, then they will be the same as extracting RES, which corresponds to that. Those will be the same. Okay. And let's compute S. Let's compute S sub x dot y. So I'm going to compute it by hand. So what I'm going to do is take the residual squared, and I'm going to take the residuals and square them and add them up and divide by n minus 2. You see the formula? The square root of, I'm actually going to compute the square root of that because I'm going to get sy dot x. Right, so I have to take the square root. So let's compute this. So this shows you how to compute it. Okay? Now, it's 4.2833. This is s sub y dot x. Where does that correspond up here? Does anyone see the 4.283? It's called the residual standard error right here. With 8 degrees of freedom, n is 10, 10 minus 2 is 8. And computing it by hand, I did here, gets exactly the same thing. Now I'm going to look at the, now the t was in the upper tail, so if I want some conclusion, I could say if I use the quantile corresponding to 0.975, then if it's greater than that in the upper tail, or if it's less than the quantile in the lower tail, which is 0.025, then I would reject. So since it's symmetric, I'm just going to say, is my t-value the absolute value of it greater than the upper tail? So that's equivalent to saying, is your t-value without taking the absolute value less than the q of t of 0.025 or greater than the q of t of 0.975? So is it an either tail? Since it's symmetric, I'm just going to say, is the absolute value of t greater than the 0.975? And so let's see what the conclusion is. What is happening? Non-numeric argument. That should work. Is n defined? N should be defined. What now? Oh, I didn't define t. Oh. Oh, okay, I didn't execute that. I'm sorry. Okay, so I'm going to compute t, and then I'm going to compute this. Okay. Sorry. So that 4.004, so where did that I'm trying to replicate a lot of the material up here. Then where is that? Where is it? Okay. Here's the t-value, 0.004. And finally, let's replicate the p-value. Now I claim that we're in the upper tail. So I'm going to take the P of t, but the P of t gives the probability I'm less than or equal to t. And the t value is the real t value. So the p value is computed as the probability I get something extreme as my value t in this case, or more extreme, which means it's in the upper tail. Since I'm in the upper tail, it's the probability I'm greater than that. So I'm going to have to subtract that from 1, but since it's two-sided, I have to double it. So when I compute this, I get 0.0039, and again, that corresponds to this. So I've replicated essentially, using R as a calculator, I've replicated essentially everything in that table. The reason I do that is because I want you to understand what's in that table and have some understanding of. Once you understand it here, we don't necessarily have to do this for more complex problems where we have to go through the detail. Well, how do you compute the standard error of this? But I want you to understand that we have to compute this estimated standard error. So for these simpler cases, we'll sort of step through this. Now let's talk about model assessment. A lot of the diagnostics we're going to do graphically. So I have some questions here. Do we have normality? So we can plot the residuals, and we're saying, are the residuals really distributed normally around 0? Remember the epsilon, we're assuming that it's II normal with a mean of 0 and variance sigma squared, so is it normal about 0? But if we're just looking at normality, a better way to do that is to construct a normal probability plot of the residuals. And then you ask, do the points lie approximately along a straight line? If they do, then we assume normality. If they don't, then we maybe have skewness, or we have an outlier, whatever. Okay, linearity is another assumption. I said that we assumed a linear model, but maybe it's not linear. If it is linear, then you would expect, maybe it's easy to look over here to read those a little bit better. So we're talking about linearity now, here, right, that line. So we're assuming that if the residuals, the E sub I, the E sub i's are the actual residuals, the epsilon sub i's are random variables, versus the y hat sub I, where we want to know, are they randomly distributed around a regression line? You know, if you have a regression line, but they sort of form a U shape around that line, then that indicates that no, linearity is not correct. Maybe you should be doing some quadratic or some more complex function of x, not just linear. And then we can also test equality of variance. As one way to do this is, again, to plot the E sub I versus either the Y sub I or x. And then, again, do the points form a band around 0 in that plot. Now, independence is something you usually know from the context of the problem. If you get a random sample, it's presumably independent. That's not always the case. So let's take a look. If we look at, I think I'll stay on this page here. If we simply do a histogram of the residuals, and I just gave a label, main, that's the main label, histogram of the residuals, you notice that it's around 0, but it appears that, perhaps there's a slight skewness to it. But again, part of the problem here is we only have 10 observations, so we're not getting a good representation by histogram. It appears that maybe there's a slight amount of positive skewness, but again, with 10 points, you're not going to get hugely strong evidence to that effect. If you plot the probability plot, however, you notice that this is, however, not, it's sort of a straight line, but there's some curvature, upward curvature. And this upward curvature, it says that the sample quantiles on the y-axis and on the x-axis are the normal quantiles, that is, the theoretical quantiles assuming a normal distribution. If that exactly followed a straight line, you would say, great. There's a little bit of curvature there. And it turns out that sample quantiles in the upper tail are a little bit bigger than the corresponding theoretical quantiles, which indicates that it's skewed a little bit to the right. And also it appears that there's a little flattening out on the lower side, down around a minus 1.5, oh, it looks like there's a flattening out, and that indicates that maybe the things are bunched up too much. So it indicates that there's a positively skewed distribution, a little bit. Probably not bad, and again, I wouldn't get too carried away with worrying about it at this point because we have n equals 10. In a real experiment, we'd have more than 10. But it indicates a little bit of positive skewness, which conforms with this. It appears like there's maybe a little bit. Maybe I should sort of draw some lines through that. Now the next one, we're testing linearity, and the question is, are the point? I've drawn a horizontal line through 0. Are the points pretty much a band about that? Well, they pretty much look that way, except for that one value, which could be an outlier. There's one large residual. Here I'm plotting the residuals versus the y-hats, and this is a way we can check the linearity of the model. And in this case, it appears that they are pretty much about it, but again, we only have 10 points, but there is one large point that expresses some lack of fit, but it's only an isolated point. And so if you had more data, you might be able to tell if that's real. And my feeling is it's probably not. It's just probably a particular individual at a certain age had a particularly high reading. That happens, of course. But if you selected a lot of people at that age, you probably would find most of them maybe are distributed about the regression line. So you had one individual in our sample that at a particular age had a particularly high value. Those things happen. But again, I think that would have been washed out if we would have had a larger sample. So I'm not particularly worried about linearity. The next thing that I'm looking at is, does sigma squared in some sense depend upon x? In this case, does sigma squared depend on age? And it's a band, again, with that one outlier, perhaps. So again, I have no evidence that sigma squared. Suppose that it would be like a funnel. That is, suppose that it was sort of a funnel where as x gets bigger, the spread gets bigger. Then that would indicate that the variance is getting bigger as age gets bigger. Now, sometimes that happens. That there's, at a higher age, there's more variability of blood pressure than at a lower age. And that, if that were true, we'd be violating our assumption. But this graph doesn't, support that. It appears that we're okay. So our assumptions appear to be okay. Well, it's about time to quit. Let me just indicate where we're heading. We've got two more areas here, which won't take the whole period next time. So you should finish chapter 9. Again, I'll get you the answers. The implication is that we're actually not too far from getting a second assignment. But again, these first two assignments aren't that difficult, but they kind of get you. And I'm going to give you a little more time to get used to R. Some of you are new to R, and so I don't want to rush the due dates, particularly on the first assignment. But here I want to get confidence bands. So ultimately what I'm trying to do is get confidence band. Here's my fitted line, and then there are two different types. I don't know if you can see these. These two lines here are what are called confidence bands on the mean, and then the two outer lines are confidence bands on a particular fitted value for a particular observation. So if I were admissions officers and I wanted to know whether the GPA in high school affects the GPA in college, and if I want to know whether the mean GPA in college, what the band on it is for a given GPA in high school, then those are the inner bands. But if I wanted to predict an individual student, those are the outer bands. But we'll talk about that next time. So are there any questions? So finish chat reading, work on the assignment for chapter 8, and as quickly as possible, I will send you the templates you can put. Go ahead and write the code, but I will send you a template you can just then put the code in. Okay. You can kind of write, right now if it says explain this, you can put the code and then put your explanation under, and so it's going to be pretty much a cut and paste this first time. Hopefully then I'll get ahead of the game for the next assignment. The other topic in answer to your question is that we will be covering correlation. And that's the formula you were probably talking about. S sub xy over the square root of S sub xx times S sub y. You have to compute all three. Or you can view it as an adjustment to B. It's a scaling of B. We can think of B being scaled to give us the correlation coefficient. You remove the units of measurements from B. because B has units of measurements of y over x. So effectively, you have to remove those units of measurements to get the correlation. Okay, any questions? Okay, again, we'll look at those next time.